So just to introduce myself, I'm Georgina Holden. I'll be your host for this evening. We've got 3 speakers today, so I'll do the start and then I'll do the questions and finish us off. But I'll just do a formal introduction for everyone. So hi everyone, thank you for joining us this afternoon for our 3rd talk for the Material Bank on stone, straw and reused steel. I know we're all looking forward to live events, and so are we. We hope that the next one that we do will be in person with you all, but for now we're very excited to be able to bring this event to you in the comfort of your own homes. This event wouldn't be possible without our amazing sponsors. So first of all, I'd like to thank our sponsors for tonight. So our patron sponsor, Alan Muir, and our other sponsors, Outro, All Good, Ibstock Brick, Milliken, Rayners, Somatic Kitchen Gallery, Forster and Taylor Maxwell. So thank you to them. So just to give you a bit of an idea about how this webinar is going to go, we have 3 speakers tonight who I'll introduce formally in a second. But while they're speaking, please feel free to send in any of your questions privately. But if you have a question that is specific to a speaker, please make sure you mention their name or feel free to open it up to all the panelists. We'll be leaving all the questions to the end of the seminar, so you have plenty of time to get them in. So, if I ask our 3 speakers just to turn their cameras on, I can allow you to put a face to the name. So we've got Rob Neild, Matt Redding and Roy Fishwick. So our first speaker is Rob Neild. Rob is from Webb Yates Engineer. He's a structural engineer with a passion for creating innovative, efficient and elegant structures, having designed projects ranging from stone staircases and timber pavilions to city centre towers, railway stations and airports. Having started his career with Arup, where he was brought up on the philosophy of total design, he now leads the Webb Yates Birmingham office based in the Drury Quarter, where he promotes a collaborative and inventive approach to engineering. I wanted to say innovative then, it's always the word, isn't it? Sorry, Rob. So following Rob, we have Matt Redding. So Matt works for Genza in the Birmingham office, and he is the European Regional Co-Leader for Sustainability. It's a bit of a mouthful. Helping to drive sustainable strategies in project delivery and helping Genza to achieve their carbon neutral goals. He was also on the West Midlands Combined Authority Circular Economy Task Force, another mouthful, working with them to influence the reduction of materials and waste on construction sites and to encourage material exchange within the built environment. Matt also heads up the BAA Green Division and has held this role for the past 3 years. And last but no means least, we have Roy Fishwick from Cleveland Steel and Tubes. Roy is the Managing Director at CST and has been employed by them since 1991. CST are a specialist supplier of repurposed and reused steel pipe for construction and civil engineering. Roy has spent the last 10 years lobbying and promoting circular economy through steel reuse specifically. So without further ado, I will first hand over to Rob, who will begin our talk about the use of stone in the design industry.
Brilliant, thanks Georgie. Can you see my screen? Is that sharing?
Yeah, that's come up. Thanks, Rob.
Excellent. So thanks so much for the introduction, and really nice to be invited by the BAA to come and talk about structural stone. And I'm also keen to hear more about straw and reuse steel as well. So I think it's going to be quite an interesting webinar. So about us, Webb Yates, we're a multidisciplinary engineering consultancy. We've got structural engineers, civil engineers, building services engineers, sustainability consultants. We work across a whole range of sectors, and we've got offices in London, Bristol and Birmingham, which is where I'm currently kind of leading the office there. We're quite proud to say that we work on quite a large range of projects. We'll kind of try our hand at anything. So we'll do anything from a high-end back extension to a mega infrastructure project. So project on the left is wooden roof, quite a modest back extension, CNC cut timber. And the project on the right is the Kilo box at Heathrow Airport, which is one of the largest capital projects currently underway down there, which is a 100 metres, I think, long, 11 metres deep basement to house a baggage hall under the taxiway. So we've got a very diverse range of person that works with us, and that diverse range of interests leads to a diverse range of projects that we do. In terms of design, everything we do is kind of underpinned by sustainability, has been since the very start, really. and materiality is super important to us. And when we design a project, we like to think about what is the right material to use, what is the best low carbon option to use. It's not necessarily always one material, it could be a hybrid or a combination. This chart really just shows a comparison between the various materials. I won't go into it in detail, but just working through from softwoods, hardwoods, engineered timbers, you've got your kind of standard steel and concrete, and also more recently post-tension stone, just looking at the comparison. To surmise from this, our mantra is kind of use more timber and stone and, less concrete and steel. I think Roy's going to talk to us about, reusing steel, which I think is, we need to see more of, and it's a fantastic way of kind of reusing a high energy material in a much better way. So not to say that steel and concrete are that bad, they're always used, but we always look to use low carbon alternatives. So stone, what do we currently do in the building industry? It currently takes a lump of limestone straight out of the quarry, could be 100 newtons a millimetre square in strength. We then crush it up into gravels and aggregates, or we burn it and turn it into lime and cement. We then take it to a batching plant where we mix it with water and we mix it with sand and other admixtures. We then put up a load of false work and timber formwork, put in a load of steel reinforcing bars, put the release agents on, pour the concrete, wait a week or so, strike the formwork, and hey presto, you've got a structure. It's now only 40 newtons a millimetre squared. So we're kind of starting with what is quite a naturally occurring abundant material, and turning it into something that is way weaker. So if you think of stone as an example in that same journey, you dig it out of the ground in a quarry, you take it to the stonemasons, shape it and hone it, and make building elements that are as strong as they need to be on day one, deliver it to site and build your building. So much lower carbon, much lower process. In terms of strength comparison, it's got a much higher tensile strength than concrete, so it's much better in shear and bending and torsion, so you need less reinforcement. Much higher compressive strength, 2, 3, 4, 5 times the strength of a C40 concrete, and it's also stiff as well. It doesn't have the embedded water from the kind of concrete mixing process, so it tends to be a lot stiffer than concrete, and you don't get the same effects of creep over time, which are always really beneficial. One of the problems with stone is it's a naturally occurring material, and it can be quite variable, so we do have to use quite high factors of safety. This ammonite was found in a test sample that was tested in bending, and probably reduced the capacity by about 30%. You couldn't see that on the surface, so you don't know that impurity is there at the start, so you do have to take account of that. And over the last 15 years, we've built up a huge quantity of test data and experience. We do bespoke tests on all the stone we use on all of our projects. Quarries will give you an amount of data, but you kind of need to go through this testing regime to ensure that your stone is strong enough. There's no real strength grading for stone like there is with timber and concrete and steel. So bespoke testing is the only way to go. And yeah, how did we kind of get into working with stone in the first place? It was really through designing staircases. As I say, we work on many projects, but sometimes we'll be working on just a small part of a very large project and doing a stair. And we started designing traditional cantilever stone stairs with a firm called the Stone Masonry Company many moons ago, and we were putting basically posh stone staircases in mansions in Mayfair. The traditional stone stair, it's not actually a cantilever, it's a torsional stair. You build the tread into the wall, that resists the torsion, and the vertical load tracks down the treads, and the eccentricity you get that causes that torsion is resisted by the wall. So very straightforward type of structure, been used many times through the centuries. Difference is now you've got to do building control calcs to prove that it actually works. So through this process, we did some fairly standard stairs. And then we started playing around with geometries and load paths to, architects were getting more adventurous, clients were getting more adventurous with what they were asking for. So these are all variations on a theme. Some there just have a kind of very raw quarry finish to the soffit. Some have open treads, so we're transferring all the vertical force at the end. The one on the right is kind of a reverse cantilever stair where we actually hang up the vertical load via a steel strap up to the top. So many variations, but all on the same theme. This was a sort of combination of a sort of traditional cantilever stone stair and I guess a kind of stone masonry arch. So using two very traditional forms, but marrying them together. This is made of 9 blocks of solid travertine. We've hollowed it out because of the weight. This is on the 3rd floor of I think a 1950s reinforced concrete apartment building to create a duplex. But there's no mechanical fixings between the joints. Everything's done with notches, hidden notches and shear keys, and everything kind of interlocks together to sort of create this wonderful piece of sculpture. Very simple and elegant from the outside, very complex in terms of the inner workings, but again, this is just pure stone masonry. If we don't have a wall to build into, not every staircase is right next to a wall. We had to look at ways of reinforcing the stone. So this is a straight flight, reinforced treads, literally 3 reinforcing bars through drilled holes up the middle of the stair with anchor blocks at either end, and works in much the same way as reinforced concrete. The only difference here is that each tread is an individual piece and it's kind of pre-cracked. The problem with just simply reinforcing it, if you put too much load on it, those cracks start to open up, which visually isn't acceptable. And also if you're outside, might cause degradation, corrosion of the reinforcement inside. So we were sort of testing ways of pre-stressing or post-tensioning the stone. The good thing about using stone for post-tensioning is it has the strength on day one. You don't have to wait a week or 2 weeks for the concrete to cure before you can stress it. You can stress it straight away. By putting a pre-compression into this run of stone elements, any tensile forces that you get from the bending of the member are counteracted by that compression. So actually those cracks don't start to open up, and you can achieve much better span depth ratios, much higher stiffness, much shallower sections by post-tensioning it. We put this to the test. This is I think a 3.2 meter long span, about 50 mil deep. So I mean, similar to basically getting 5 paving slabs and post-tensioning those together. There's 2 cables which are routed into the underside and anchored into these anchor blocks at the end. And this was designed for a kind of standard domestic floor loading. So it just shows the potential and the power of using such a material that's so strong in compression, using it in a more innovative way, the same as you, Georgie, inventive way I'll use instead, with the cables and the tensioning to get a really nice balanced structure with minimal material. And then here you can see there's kind of the cables routed into the underside and then kind of disappearing in. And the reason they were routed, it's very difficult to kind of drill holes, straight holes through quite thin sections of stone. We tuned up this technique into kind of stairs with a bit of a curve on them. The standard reinforced approach wouldn't work here, so we post-tension these. And this was the sort of eureka moment of being sort of pushed by the clients in terms of what they were after, and pushed by the architects, but also pushed by the stonemasons to imagine how things might be and how things might work. So this is a almost 270-degree helical stair. It's got 2 post-tension strands down the middle, both cranked up to about 16 tons each. And you just get this really lightweight, elegant structure, 2 very simple materials and a reasonably simple process. I guess the analysis process isn't simple, and we've built this up over many years of trial and error. We build physical models to check concepts and see if broadly they're going to work, almost a proof of concept. So we 3D printed each tread. We fed some bicycle brake cable through the treads, and we tensioned it together. And this worked quite well in the office, so we thought, great, this must work at full size as well. We've created parametric scripts to create the geometry for our analysis models. We carry out quite sophisticated 3D brick analysis of the stairs to check all the major stresses, to check the deflections and check the cracks. But also we back this up with full-scale tests as well. This is in Stonemason Company's workshop, and this is a full-scale load test, cranked up to the full load. You know, you learn a lot through doing the testing. The first time we tried it, it went a little bit wrong because the stressing sequence wasn't followed to the book, and we overstressed one side of the stair rather than do it in quite a controlled sequence. And the stair kind of, for want of a better phrase, exploded, which wasn't great. But actually the learning you gain from that, you're able to use a bit of trial and error, redo the test, understand why it went wrong, and build that into the design and the construction as you go forward. And the end product sort of ended up being quite stunning. This is a variation on the same theme. This was born out of an architectural concept of a kind of whale vertebrate. Others call it the dinosaur stair. So the treads aren't all fully engaged. There's internal steel reinforcement in some of the treads here, and we'd use structural adhesives to hold the stair together and prevent some of the twisting. But again, very similar concept. And then this is probably one of the largest that we've done to date, which is, I think this is in Turkey. This was with Foster and Partners, and this is a full 270-degree helical stair. And this is also in quite a highly seismic zone as well. So we have to design this stair to, you know, to hold itself up and stop, you know, prevent it from shaking apart in an earthquake. So all that learned, that staircases. So how do we kind of amplify this up into building design? This is 15 Clerkenwell Close that we designed with Amin Taha architects. And this building was initially conceived as, well, it had a few options for the facade. One was a parametrically designed steel exoskeleton. Then it turned into more of a traditional masonry building to fit in with the kind of local vernacular. But when I say local vernacular, it's sort of the more contemporary vernacular in terms of this is right opposite a stone church building. There was an 11th century Norman chapel on the site, again built out of stone. So actually what you see when you look around the area is these almost fake brick clad buildings. They're not brick load bearing buildings at all in the traditional sense. They're concrete or steel frames with bricks hung off them, with all the fixings and the joints that comes with. So the intention here was to go back to basics and actually use stone in its true capacity as a load bearing material, the same way it's been used for, you know, centuries and centuries. It's essentially a reinforced concrete flat slab building, an offset core to the rear to give it stability. The construction sequence was slightly odd and was kind of frowned upon at first, but the intention was to have one trade build up the concrete, back prop the lot, bring in the stonemason to put in the load bearing facade, stitch it all together, take out the internal props, and hey presto, it remained standing. That actually saved a lot of hassle and was a quicker program than just doing one floor of load bearing stone, then the concrete, then the stone, then the concrete. So again, thinking through construction sequence as well as the materials and the structural typology is so important to kind of deliver a structural project. And, you know, the carbon saving in this was significant in terms of the sort of perimeter facade structure. Obviously, with an exoskeleton, you have to think about cold bridging and thermal break details. This is a kind of bespoke detail we came up with, but essentially exactly the same as the principle of a cantilever balcony on any residential building you'll see up and down the country. And again, just some of the final details. So this kind of gets us thinking within, you know, Web Yates, where has stone been over history? From, you know, way back thousands and thousands of years when we lived in stone caves. You know, when they built Stonehenge, although we look at it today and it's just a few blocks of stone, the technology and the management and the planning that went into that must have been so far ahead of its time. Also a little bit of why are they doing it? Why are they, you know, taking these huge kind of megaliths from Wales and popping them up near Salisbury? But, you know, through to the pyramids, the Colosseum, you know, Renaissance structures, into modern day structures, Padre Pio Church, in the sort of 2000s, stone ribbon bridges, fantastic project in Sagrada Familia, which is currently being finished at the moment, and within the next 5 years should have finally finished. How can we look back through history to get clues as to what we should be doing going forward, taking into account the climate emergency, having to use low embodied carbons, having to really push to do things differently and really actually reduce the embodied carbon in buildings rather than just saying that's what we're doing. So we've been working away. We're working on a kind of a larger version of Clerkenwell Close. This is a 10-storey building near Finchley train station in London. Same principle. We're looking to use the facade for stability as well, to use it as a moment frame. In this instance, the facade needs to be fire protected, so we've put some big lumps of basalt in the furnace. If you think about where basalt came from, it's quite used to very high temperatures being sort of metamorphic. So, you can imagine in terms of fire, it passes with ease. There are other concerns with fire that I'll go into in the next few slides, but it just shows how you can take a small concept. We've gained the experience in the material and we kind of scale it up, produce another building, show it's possible, scale it up again. And through all of this, we're working with a set of designers, a supply chain, a set of other consultants that build up a skill set in this and actually create a kind of legitimate supply chain for this. One of the big barriers for stone in the current industry is the likes of steel, the likes of concrete. Our industry has grown up to feed these other larger industries. There's like an inertia to changing and bringing new products in, but with the right direction and the right examples, we feel that there really is mileage in more load-bearing stone buildings. How can you scale it up to use the stone also for your floor plate? So this is an example of a typical bay for a commercial building, 12-meter span, double beam with a kind of integrated stone slab on top. This is designed for full commercial loading. This was on show outside the building centre during the first lockdown, actually, so not the best time to put an exhibition on. But we've designed this beam in theory. We're taking this to UCL to load test it at this scale. But we think with enough kind of research and development and continuation of this same theme, this could be scaled up to a 30-storey building. This is an example that just shows the building in the foreground and how it would sit in the City of London, using stone columns, which the size of the columns is reflective of the load on them, using either load-bearing stone or CLT internal structure with either a concrete core or a post-tension stone core. We worked with an architect, we worked with a quantity surveyor to analyse this building and sort of made a proposition that this might be, although slightly more expensive today, if a supply chain developed and there was more knowledge and more capability, then this might well be a cheaper way of building and certainly much lower carbon into the future. So we've kind of taken this a step further. So we're working quite closely with UCL, with some PhD and some master's students. I've actually just come off a call with Wendell, who's the guy in the background in the top photo with the camera, to discuss the projects that they're going to do this year, which help us with our research and development. This is some testing of some post-tension stone beams to failure. This is rather on the same day, happened to be the hottest day of the year last year in the car park. We managed to get this fire up to about 600 degrees and stuck the beam in it for about an hour and a half until everyone got bored and wanted to go home. But it stood up very well. We had thermocouples in to understand the heat transfer throughout the beam. And it was a really good proof of concept to show actually, with all the kind of current fire regulations and this whole onus in, very, I guess, cagey fire strategies and, so important, but this really showed us that there's real possibility to use this internal for fireproof structures. This is the latest. This is kind of hot off the press, pardon the pun. This is from a couple of weeks ago, a huge facility in France for another project we're working on. This is a 6-meter spanning beam, 100 kilonewton point load mid-span. This was cooked in the oven essentially 3 hours at 1,000 degrees It started to crack about 45 minutes, but then absolutely withstood everything the fire had to throw at it. So we're currently in sort of post-analysis of these fire tests, but again, really encouraging signs that this has really got legs as an alternative to concrete in terms of inherent fire resistance. And really just to finish on a bit of a kind of suggestion, really, that, you know, if we think about what the world needs, the whole world needs in terms of built infrastructure. If you gave every single person on the planet, so 7 billion people, if you get every single person a 5 by 5 meter slab, 200 mil deep, 5 meters cubed total of material, that would equate 35 kilometers cubed of stone. If you think about in terms of sustainability and renewable resource, that's an absolute drop in the ocean in terms of the volume of the Earth's crust. To put it in perspective, that's 35 kilometers cubed. That's about half a Ben Nevis. So we could build enough building for the entire world population with a Ben Nevis, you know. So, and it is constantly renewing. Obviously, takes time, but it's totally abundant. And yeah, I don't think supply would really be an issue. I think as well, this is just an image from a limestone quarry in France. You know, people are saying, well, we don't really want to go digging up all our beautiful countryside to extract all the stone. We'll have huge kind of scars in the landscape. So, you know, this is a huge quarry in Leicestershire that, you know, may be a bit of an eyesore and a scar on the landscape, but quarries can be beautiful too. Once you've got all the kind of usable high strength stone out of it, that's been extracted, give it back to nature, you know, turn it into a beautiful lake, huge opportunities for more biodiversity. And I think it just goes to show, really, if you follow that through, it's a method of construction that can really kind of sit well with our kind of planetary limits. So important, and hence why we continue to push it. So yeah, that's all from me. I will stop sharing and I'll hand over to Matt.
Thank you, Rob. That was awesome. That was really, really interesting. I loved it. Especially the beam stuff. Very, very cool. Let's see if this works. Can you see that? And can you hear me?
Yeah, I can see you and can hear you.
Lovely. Right, so I'm going to try and, or certainly, hopefully not fly through this too quickly, but for me, this is straw. I'm going to be talking about straw. Thank you very much, Georgie, for the lovely introduction. I just throw this up here so that for those of you watching on YouTube and skip through the first 2 minutes, then there I am. But ultimately, really passionate about low impact materials, and I really want to. I know what you're thinking in the regards to we've just had stone, so now that we've got straw, that somehow we might have somehow wandered into some kind of children's storybook. We haven't. And no, straw is not one of those ones where you can huff and puff and blow it down. Certainly not when it's compressed, but just wanted to, I think it's probably one of the most damning children's stories for straw, but moving on. So I just wanted to kind of make you all think a little bit in regards to what's out there in terms of straw buildings. I'm sure that some of you might be aware there's quite a few, or you might be aware there's not quite a lot. So the European Straw Building Association public records, which country has built the most straw bale buildings in Europe? So any guesses, having a think? Well, if you guessed France, well done. Yeah, they have on their records, they have 600 buildings. France has a huge government sponsorship for straw buildings. There are a lot of them in France. And now remember also that these public records are just ones that people have filled in. This isn't all the numbers. There's probably a lot more, especially across the continent. So these are kind of take with a pinch of salt. Next on the list is Austria. 164 buildings, and then coming in third place is Germany with 73. And if you're wondering about the UK, we don't come in till with 43. Now, granted, again, pinch of salt. Not all buildings built in straw are recorded because a lot of them are single home kind of home builders. They're the people who are building their own house, so they're not necessarily on public record as being built in straw. But you know, it gives you an indication. So let's talk about a few different construction methods with straw. Now, the first one is load bearing. Load bearing is basically you stitch the bales together in a stretcher bond, and then you compress them, and that's what you're seeing there on the screen. That kind of picture, the bales being compressed. And you're probably thinking to yourself, that doesn't sound very stable. I mean, it's just you're just relying purely on the straw, taking in that structural capacity, as well as also, performing a number of different jobs. If you think about wall insulation or a PIR insulation, it doesn't also do structure. It's just purely insulation, whereas this is doing both structure and also insulation. Well, welcome to these council housings in Waddington, and they are, they were built in 2009, 2010, and they are two-story load-bearing houses. So these are completely made of straw, and you'd have no idea. Maybe the slight curved render on the corners might give it away if you were looking really carefully at them. But yeah, these are built from load-bearing straw. They're a first in the UK, certainly, but it's just really amazing what you can get to kind of the finish and quality using straw, and you'd never know. You could walk past those buildings and you'd never know that they were built of that particular material. And that's what I've tried to include in this presentation, because I think when people do think of straw, you think some kind of very handmade, kind of like almost a crafty, artsy kind of style, but actually you can get a very modern finish using it. Having said that, moving on to our next one, which is infill. So this is where you use straw basically as just the insulation. It's not being used as structure. It's being used to infill around a structure that's built for it. So timber or steel or whatever. It's purely just that's its purpose. So this is one of the buildings I've worked on. It was a house in Belgium, and this is probably my own. Well, it's one of two kind of very crafty looking buildings, so I couldn't help but put this one in. I really enjoyed it. It was a great little project. Working with roundwood timber, working with the straw, and then clay renders on the outside and inside. So a really interesting one. And again, you're looking at essentially a frame and using the straw as insulation. You do have to think about how that insulation is taking up, because at the end of the day, you are working with a small bale, which is about 400 wide. So, that's the kind of really interesting. That's how info works. Moving on, there are prefabricated panels. And this is where straw starts to take on a very modern look at being used. There's two that are currently commercially available within the UK. Ecococon, and I'm not too sure if I'm saying that right, but that's how I've always said it. So Ecococon and Modcell. Now, the interesting things between the two is that Ecococon is made by blowing in the straw into a timber frame structure. So previously we've been talking about kind of small bales that a small baler would do, whereas commercially available, they're much larger. You probably, when you think of a straw bale, you might think of something that's round, or really, really big straw bale. So what Ecococon does is it basically takes that bale, kind of, takes it apart and then blows it into this timber frame. And that's that's certainly one way to do it. And it obviously means you can use any type of bale. Modcell, it's a timber frame. It's rather than it being just a kind of wooden frame, it's more of a wooden box, and then infilled with, again, in tension, straw bales. You can do some interesting things with mod cell, and I do give an example a little bit later on. But yeah, a really that mod cell is one of the great things about mod cell at the moment, is that it uses this thing called a flying factory, and so you can build mod cell in a local essentially farmer's shed to the site, so you can really reduce the construction to site kind of distance between for material. And the really great thing about this is that you can get people involved. If you're building a community center, you can have people of the community come in and help build part of their community center. There's a real opportunity there for really great community kind of engagements, and being part of a building, or being part of the construction, really helps people to connect with that building. So on to so a couple of examples. So we've got my personal, and that if you haven't heard of this particular project, Lilac, which is in Leeds. So you should absolutely check it out. It's a really amazing project. It was built incredibly quickly and all using mod cell, and you wouldn't really know. It's a very modern look that they got out of it. I've immediately forgotten all of my notes, but looking down at my papers, the Lilac development captures and stores over 1,080 tons of atmospheric equivalent CO2. So it's a huge environmental kind of, you know, it's amazing. I think it's just such a great project, and do check it out if you are interested in that one. And then Ikokacon. So Ikokacon, this is a gym. I'm not going to attempt to name that. No, I'm going to give up immediately. So again, you can kind of see these timber frames of Ikokacon just being built into the structure. This was built in the Netherlands, and again, a modern building, a modern use, something that is not just residential. It's not just for something that is for single home house builders. It's a modern construction. It's basically large Lego bricks. It's being stacked together. And then also one that's a little bit closer to home, the Gateway building in Nottingham. This is essentially is a mod cell. You can kind of tell, but instead of it being kind of several bales stitched together inside of a frame timber box, it's just one bale stacked on one top of another, and in that timber frame box. So yeah, really interested. Make did this. This was a really interesting, interesting kind of showpiece to show off straw. And I think if ever you're around in the neighborhood, do check it out. It's a very cool building. And then onto another construction method, which is big bales. So big bales are the ones which are commercially available. Granted, not the round ones. We are talking rectangular. And they are heavy. You do need a crane. And you're probably thinking from this photo, you just built the pyramids and then whacked on a roof light, which kind of true. And you certainly wouldn't guess what the finishing look would be, but this is it completed. And I think again, this is an exhibition building. It's based in Zurich in Switzerland, and I think one of the great this is a great example of really what you can achieve with this material. Yes, it's it can be complicated within the detailing, but actually you can get a finish on a building like this, and you can really push what is capable. And I particularly like this project for its its unique style, and certainly from that first picture, you'd never know that that was underneath that cladding. So and then moving on, I couldn't help myself putting a little bit of a crafty. This is the second one of hybrid construction of straw. So that's where you're using a mixture of a few of them, where it's either infill and it's a bit of structural load, or it's using some paneling and then infill. But ultimately, there's not all straw buildings have geodesic domes. They're not all these kind of very green, very kind of very and while very beautiful and nice, they can also look incredibly modern. They can be things which are sharp and that can be used in a very modern way. And I think that's something that I'm hopeful that you've kind of gathered over this presentation is that straw is not something that just is a miscellaneous or is a kind of a old-fashioned construction material. It can be very much a modern material when used correctly. And so really we come to my end of mine, but just to encourage you, if you were interested, I would highly recommend checking out strawbalebuildinguk.com and strawbuilding.eu. They are great resources of information. They're really, really key. I highly recommend Barbara Jones's Building with Straw Bales. I do own a copy myself, but I'm not on commission, so I mean, do what you like. But I think it's just it's a really interesting book, and if you were trying to kind of get your head around some of this material, there is a technical guide that's coming out. It is going to be available soon. A kind of draft version, which Barbara Jones kind of goes through, is available. You can take a snippet of this when it gets onto the YouTube. But yeah, no, really do check it out. So. And that's it for straw. So thank you so much for listening, and over to you, Roy.
Sorry, bear with me. It's just decided to ditch the presentation for some reason.
Perfect.
Strange enough, I can see it on my screen, but it isn't apparently in the options to share. Are you seeing that now, anybody?
Yeah, that's coming through, Roy.
Excellent. Okay, please bear with me. I think I'm in my 8th hour of Zoom today, so I'm a little bit jaded. My presentation really is more generic. It's not about specifics. It's not about particular buildings or particular products even. It's more to do with the potential that's available from the existing building stock in real terms. The reuse argument, and please forgive me, I was asked to make this presentation sort of fairly basic in the first instance. I think probably most people are very familiar now with why reuse should happen, but one of the things I would like to point out is that there are quite a number of industries, quite a number of businesses that are claiming low carbon that already were. And if what we're trying to do is solve a climate emergency and improve the situation, taking credit for something you're already doing isn't really going to lend much to a net reduction. So that's one thing I would argue you've got to keep an eye on. We've got to see gains or losses, more importantly, in the use of carbon. The other thing which has happened much more recently, and I've been involved with this for nearly 12 years now in terms of lobbying for reuse and circular economy arguments, even with the EU. But the thing that's changed this year specifically is that customers care. I'm actually now being involved with meetings with clients that are wanting reuse in their projects. They're wanting to look at their existing asset to see what they can recover from it and use it on the next job. So a lot of audiences I talk to are quite resistant to reuse because it complicates their processes, etc. They're now being obliged to take this more seriously because clients and finance organisations are pushing this forward and pushing it through. Steel is a fantastically recyclable material. I'm sure you all know that. It's 95% currently recycled, which is why I make the point about actually making that claim isn't very beneficial going forward. It's 95% recyclable now, which means that it's not going to help the climate emergency going forward by continuing to be recycled. There are clearly a lot of investments into better energy use or more efficient use of resource to do those conversions. But the real benefit of steel is that its properties don't deteriorate, which means it's available for reuse. We have an LCA that was done for us based on pipe work, to be fair, but the calculation is very similar for sections. If you recycle steel, you're saving 70% of the carbon versus new. That's based on global average. If you reuse it, you can save potentially 96% of the carbon. So there's a very definite environmental incentive to look to reuse. I've put this slide in because there are very many levels of knowledge regarding circular economy and low carbon principles. Reuse is material that is used again. That sounds really obvious. It's material that is diverted from waste. I make that point because, as I read the other day, 13% of construction materials are thrown in a skip without ever being used. But they're still waste. They've been made, the carbon cost is accrued, and yet they're going to go out as landfill or whatever else. So your reused material can be very distinctly secondhand, or it can be a diverted waste stream. In that regard, the reuse classes for 94% as there. Repurposing is where you ideally use one product for an alternative use. One could argue that with straw, if it was intended for cattle bedding and now it's a building, you've potentially repurposed it. Upcycling and downcycling. Concrete is usually the guilty party for downcycling. You claim it's being reused because you've crushed it and used it as aggregate. There is saving in that, but it's less easy to quantify. It's not a calculation I've done. And then recycling, which is still stuck as some people's idea of circular economy. As long as it can be recycled, then that's a good thing. I would argue it is a good thing, but you've clearly got the energy input of recycling, which if you're reusing can be minimized or not there at all. In terms of can we reuse steel, this is an old argument. It's got a lot of issues to do with regulations and standards. That's how I got involved. CE marking came in 2012. The UK market was educated to understand that from that point forward, they could only build with brand new steel made to harmonise standards. It isn't actually true. The construction product regulations allow for sustainability. And in fact, I've just found out in the last few days that the SEN committees are now actually looking at changing the CE marking standards and the construction standards to allow for reuse specifically, and to also push specific methodology. So in the 10 or 12 years I've been lobbying, the situation has changed markedly. I would love to think down to my efforts, but I suspect not. If you're wanting to get into the reuse situation, or if clients are pushing you in that way, there's a number of things that you need to consider. The main point, and it's very important currently, it's a developing market. So if you need 1,000 tons of reused steel and you want to go out and buy it from a trader, you've probably got a problem. I've got 70,000 ton of tubes. If you want pipe, that's not such a big deal. The other problem with reuse is flexibility in design requirements and specifications. If you specify everything to S355 J2, which is a very modern steel grade, or worse still S460, anything being taken down will be older and therefore will probably be a less strong grade, as that's the nature of evolution of product. The older products are generally a weaker grade. The other thing with reuse is don't go all or nothing. I've seen a lot of academic studies which suggest reuse isn't viable, isn't feasible, but they basically look at entire buildings coming down and then look at the opportunity to reuse all of the content going forward. It's just not practical. It's not really common sense. And at the moment, we're looking for step change. So even the small step helps. So some reuse is better than no reuse. Look at what's available, look at how it can be used, and you'll gain the benefit in that way. One of the main pushes we're seeing at the moment is on the steel assets you already have. So there are large businesses, large companies in London, particularly property companies, that are looking at buildings they're taking down and now actually specifying that they want to see those materials going into the new building. It poses various problems, but it's those problems that we have to address and solve. If you don't have use for your own materials coming down, look at who might want them. Don't just throw them away. Don't just commit them to the normal recycling or disposal routes. See if there might be somewhere it can go. Somewhere it can go and be more useful. In the last just literally 6 months, this is really happening more and more. I'm involved with 3 or 4 pilot projects now that are looking at steel reuse, either from existing buildings or from a small inventory that I've built up. And we're sort of addressing the more technical issues of design, etc., as we go through those projects. One of the things that frustrates me with all of that is that refurbishment is something that everybody does without batting an eye, which by definition uses the existing asset without question, might do a bit of testing, a little bit of calculation, and off you go. People will do that with massive structures without any reservation. And yet you suggest using what would be basically the same steel in a new building, and everybody lays an egg. So there are just conceptual barriers to overcome. If you're looking at doing this, there's a document we sponsored that the Steel Construction Institute produced, and it's a reuse protocol. So it talks you through how to assure fitness for purpose, basically. How do you ensure the materials you're getting are going to be fit for the task? If anybody wants to drop me a note, I can send hard copies, but it's also available on the SCI website. Gets quite technical and engineering at the back. It loses me at that point, but the principles are absolutely solid. In terms of reuse and where it has occurred, our most famous job will be the Olympic Stadium. We don't do the fabrication, I might add, but we put 2,000 tons of Irish gas pipe, which was waste, believe it or not. So that was material that had been bought for a project, and it was the overproduction. So that would typically have just been cut up and scrapped, because oil and gas pipe is really project specific. So if it doesn't get used on the project, it's usually disposed of, because you could be 10 or 20 years waiting for another job that requires that self-same material. So there was 2,000 tons of gas pipe went into that. Even as a conservative estimate, that would have been 14,000 tons of carbon saved. Sorry, I'm getting carried away, 4,000 tons of carbon saved. This is a project we did ourselves. It's our sister company's building, and this actually demonstrates the benefits of reuse financially as well as in terms of carbon. So we required a 12,000 square metre building. There was a frame came up for auction. It was a cancelled order. The frame had been laid in a storage yard for about 6 years when we got it, and in fact we had it laid about for another 2 or 3. We were required to replate all the columns at the base, to stiffen a column row. We added crane gantry brackets and haunches, but the steel frame itself was basically a commodity redirected from scrap. The other savings we made were in making sure that the ground level was the most efficient for muck shift, so we moved almost no material from site, and we used road planings instead of bought in aggregate. So this is stuff taken from the motorways locally when they were resurfaced. We used that for underneath the concrete slab and for underneath the roads around the perimeter of the building. The net effect of those efforts was we saved 1,500 tons of carbon, but in terms of the more traditional approach, we also saved almost £1 million in cash. This was a built project of our own, so it was our own incentive to make these savings, so we were well motivated. And that got us through some of the problems that we had going along the way. But in truth, it really wasn't that difficult as long as you were open-minded to finding solutions rather than just thinking of problems. In terms of our specific business, I've put this at the end, it's probably less interesting for you all really. But the oil industry generates huge volumes of pipe. So at the moment, there are 3 currently cancelled projects, 600,000 tonnes, 375,000 tonnes and 60,000 tonnes. If you allow for steel being 2 to 3 tonnes of carbon per tonne of steel. That's colossal. But these are jobs that have just been cancelled, that the material now has no home to go to. So fundamentally, it's wasted. It's mind-boggling, it's appalling, but it's the situation that has been very similar for quite a number of years. In terms of strict reuse, second-hand material, that was commonplace for our business 30, 40 years ago. But clients have changed their expectations. There are cosmetic demands on product that's probably never even seen. We do a lot of piling, it gets knocked in the ground. Does it really matter if it's cosmetically inferior? Practically no, but it does if the client won't sign it off and pay for it. So the market has increasingly migrated towards more and more cosmetically demanded material. If you're interested in tubular materials, there's over 500,000 tonnes of second-hand and surplus downgraded waste oil pipe available in Europe. Some of it's second-hand casing from the oil industry, so it's what we call downhole, that's been pulled out after use. Gets used a tremendous amount in micropiling. Yeah, in terms of us, we've been around for 45 years. We've got actually 80,000 tonnes of steel pipe now at the moment. It's 100% traceable, so we can identify the unique characteristics of every pipe. We can do material testing. We can validate the grade, the strength, all of those good things, and obviously the dimensional checks are pretty straightforward. We can also prove the welds where it's welded. That's 80,000 tonnes for you, basically 100 acres. Looks actually more impressive when you're walking about among it, to be honest. We're able to store that material, but also process it. So test it, blast it, paint it, cut it, weld it, the whole 9 yards. So if you're needing columns or tubular work, by all means, give me a shout. That's an array of material. So material that's been decoated, you can see the material that we've cut samples from. You can see provenance on the material in the stenciling. You can also see my copper spaniel sitting in one of the biggest pipes we ever had. And that's me. I think probably more or less on the 15 minutes. I'm very happy to field other questions. Otherwise, I'll hand it back.
Thanks very much, Roy. Thanks for all our speakers, I suppose. We haven't got that many questions, but I'm just going to run through a couple that we've received. So I think there was one originally that was given to us through the Eventbrite, and the question is, I believe this is probably to everyone really. It says, what are the tools and guidelines you are referring to for the analysis of embodied carbon and material selection? I don't know who wants to go for that one, which is a bit tricky because obviously it's a question pre the presentations. So if anyone wants to give it a go, let me know. If not, I'll go on to another one.
I think I can probably dive in on that one, Georgie. And thanks to Roy and Matt, really interesting talks as well, even for myself. Can't help thinking that was a sales pitch to get rid of 80,000 tonnes of steel, Roy.
We don't need any help to we don't need any help to shift it at the moment. The market's mental.
Brilliant. I think, yeah, in terms of, I think over the last few years, a lot of different companies have produced their own tools for basic counting embodied carbon, but in my view, it's just kind of it's not that difficult. You just work out the volume, which is very easily done by the Revit models that we have now, or even if you're at a concept stage, you can do a typical bay or a typical part of a structure. And then as long as you're using the right factors, you know, Bath University Carbon Inventory, Institute of Civil Engineers Carbon Inventory, you know, times one by the other, and you can kind of get the answer out. There's obviously a lot more complication in that, doing it through the various stages and, you know, transport, what happens after the end of the building life. I think there are some sort of bespoke, commonly available products that you can get. Someone else might be sort of best averse to suggest what they are. Maybe you know, Matt, but we tend, certainly for the structural side of things, we tend to use our own kind of in-house calculation methods.
Just
Yeah,
to butt in, as far as I can tell, if you go back 3 or 4 months, there was a sort of rush into the market of various carbon calculation tools. So I know the BCSA one have got one for structural steel. I know that a couple of the large contractors actually produced their own tools and made them available. I'm not sure if BRE haven't also got one that's really very complicated. One of the things I would countenance, however, because I'm seeing this more and more in our sector, is people have to remember this is a global crisis. So what you tend to see is people trying to specify the lowest possible solution for their project, which becomes very restrictive in the specification. But if all you've done is take the most carbon reduced material and everybody else has to have the other stuff, the impact isn't what you think it is. It's just good for your job. And I accept that's a commercial reality, but we do have to remember, it's like the example being specifying recycled content for steel. There's only a limited supply. By all means, put pressure on the suppliers, but if you're buying it, somebody else isn't getting it, the net effect for the climate is nil. And that's, to me, an important perspective to maintain.
The kind of, I mean, the calculations and calculators that I've seen for European is one click, LCA, and Tally. Tally is more American centric, but still universally workable. But yeah, those are probably the two that I know of as being certainly mentioned in the London future for the planning requirements of providing a whole life carbon assessment. So yeah, there's definitely there's a few out there, but it is a bit of an infancy and wild west. There's no kind of like, it's not like an ISO where there's a standard way of measuring those. So I don't know if that helps, but certainly those are the two which I'm familiar with.
I think I just add one more thing on that as well, is that I and many people have been saying for a long time, until legislation changes, until there's a statutory requirement to minimise embodied carbon in projects, people won't. I'm hearing it's coming through some planning processes that local authorities are suggesting you won't get planning unless you can prove it's a certain number. Yes, there'll be a lot of fudging of numbers because it's a calculation which is in its infancy, but people have to start doing the right thing. I think the best thing I've seen recently, Will Arnold, who heads up the iStruct sustainability sort of climate change portfolio, has been instrumental in pulling together Part Z, or a proposal for Part Z of the building regulations, which, it's kind of what they did with Part L years ago to reduce the amount of energy and increase the air tightness and insulation of buildings. But this is a proposal to actually set limits on your new build to really make people think about actually doing it rather than talking about it. And the more people that throw their support behind that, companies, individuals, whatever, is going to be more beneficial.
I think that's what I'm finding as well. It's kind of coming from more individuals because the policy is not there, so people are just making it happen instead. I'm finding that a lot. So I've got another 2 questions. So these are directed for you, Matt. I don't know if you're going to know them, but you might be able to direct us to some sources that might be able to provide us with the answers. So the 2 questions are, how much is a straw build compared to traditional? And what is the lifespan of straw builds?
Well, I'll start with the slightly harder of those 2 questions. The first one, which is like, how does it compare? So the 2 council buildings, which I showed at the beginning of the presentation, they cost 103,000 per house, and that's from the foundations up and excluding the porch. So if you're familiar with some of the traditionals of some of the costings for commercial kind of council housing, then you'll kind of have an idea about where that sits. But in general, it really varies. The reality is that at the moment we've got an issue with the amount of wheat straw that's available commercially, and etc. It is variable. So I would definitely check out the kind of links that I sent across for the UK straw bale and the EU straw bale associations. So they're great sources of knowledge, and will be able to get you a bit more of a in the ballpark region. And the easier question, which is how long do they last? We've got straw bale buildings lasting up to 100 years. Keep them dry, keep them uncompressed. They'll last as long as that happens. You know, at the end of the day, you know, straw is a dead plant, really. You know, essentially, it's the waxy material, so it will last a very long time. I mean, you spread it out and you expose it to lots of air and water and moisture and soil, it will decompose, definitely. That's the great thing about a natural material. But otherwise, if you keep it dry, keep it in the wall, it will retain all of that embodied carbon and in the actual walls.
Great, thanks, Matt. I suppose that these are kind of probably personal questions from me, but this is probably one directed more to Rob. So I suppose it's almost more of like a challenge question, but could you technically build a whole building from stone, like a whole house? Is that a possibility?
Yeah, I mean, absolutely. I think, you know, we built with stone for centuries and centuries.
Yeah.
And then we started building with timber, and then we had the Great Fire of London, and then we started building with brick. And then, you know, Industrial Revolution, steel and concrete came along, and everyone sort of flipped onto using those, you know, for very good reason at the time. But, you know, the industry is geared up for those materials. Education is done in a way that people know how to design in those materials. Go and find someone who can design in stone. There's very few people who can do it. You know, Clerkenwell Close shows that, you know, we're making parts of buildings out of stone. We're working on another project, big private residential house, and yeah, we're trying to do as much in stone as possible. So we've got stone vaults, we've got stone arches, we've got stone basements. You know, why sometimes the most embodied carbon in a project is a basement, because it's generally going to be 250, 300 thick concrete walls and a concrete slab. But why not just put in some reasonably massive stone structure, find some good, strong, cheap stone? You're not going to see much of it. So yeah, entirely possible. And that's what we're sort of pushing. We're also kind of pushing hybrid structures, where using stone in conjunction with timber and using the compressive properties of stone compositely with the good tensile properties of timber to create sort of building systems where you're mixing and matching materials, but making the best out of the properties. So yeah, it's entirely possible, and I think you need clients with desire and vision. You need sort of architects that are keen to push it, and also, I guess, to go on a bit of a journey through design. You know, if we all had more time to design and think about things, so we get a better product at the end, rather than screwing programs down and getting everything out the door, so we have to do what we did last time. We spend a bit more time thinking about things, testing things, researching things. Granted, you can't do it on every project, but for something that's going to be there 50 years, 100 years, we should really put as much design thought into it as possible, rather than just churn out what we did last time.
Yeah, I completely agree. And I think as well, it's just going back to those basic kind of traditional materials, like you say as well, and just remembering what is possible with them and then pushing it further now that we have kind of new possibilities with everything that we've used before. So I think Matt has a question for Roy.
I do. Roy, I have a question for you. This is a conversation which kind of came up recently for me, but so that it was I was speaking to someone. I was saying, oh, we could reuse steel, and they were like, oh, you mean like, you know, melt it down and reform it? I was like, no. I mean, as it is, and then put it back in. How do you kind of get around a conversation like that? Like when you're talking about your kind of your reuse steel, as it were, because a lot of people know that it's reusable, but think about it in a way that, well, I can take the original product, I can melt it down and form it into anything else.
It's an education piece, unfortunately, and I say unfortunately, it's why I put the daft slide in about language, because I got to be honest, I was at an ArcelorMittal presentation in the heart of London in one of the really big snazzy buildings about 3 years ago, and they'd flown an American circular economy guy, I can't remember his name now, but he gets paid a fortune, very eccentric. But the American model for circular economy was all about recycling. As far as they were concerned, it was a circular economy as long as you could take the product, melt it, degrade it, and then reform it back to the thing it used to be. Whereas for true circularity and for the real benefit of the globe, essentially, then the reuse is a far better thing. So it's making them understand that they can have the same thing reused as new, and explaining that what they're perhaps proposing in the reuse is already happening, so they're not really achieving anything at all. And those would be the 2 points I would really use. But the other thing is key is actually getting the design and specification right early doors, because one of the biggest challenges with steel reuse at the moment is you can't really introduce reused products after design is finalized, because there isn't enough of it available. It's not likely to be there when they need it. And yet there's a huge resource in terms of what's getting demolished and scrapped currently. I don't know if that was even an answer, but I tried.
Yeah, no, definitely. No. It was an eye-opening kind of conversation where I'm talking in one way. I'm talking about reuse steel as is. You know, you take it out of building, you then put it back in another building, and they were thinking, yes, you take it, you ship it somewhere, it then gets melted down into what we need, and then we get it back as this.
I'm aware of a very large
material.
project at the moment that's actually promoting that particular philosophy, and it's bonkers. Because to counter it completely, what's the difference between taking your material and melting it and turning it into something, and taking any of the other 95% of steel that currently gets melted and turned back into something? You've achieved absolutely nothing. In fact, what you may have done is made your scrap travel further, depending on what would have happened otherwise. But the basic thing, and it's very, very difficult, because there are people who are educated and specialised in the sustainability arguments, and there's the rest. And, and it's where you start this conversation from is so difficult. And that's even from people that are willing to buy in. And it's very difficult when you do presentations like this. It's even more difficult when you're just talking to clients in the first instance. Because the biggest problem with clients is some of them are actually telling you they want to do this stuff, but they don't know what this stuff is, which is a bit what you're alluding to. Yeah.
That was great. Thanks, Roy.
Thanks, all. I think that's all the questions we've got. So all I'm going to say is thank you, Rob, for showing me that incredible travertine stair in central London. That was beautiful. I think, I was so glad I was on mute, because I was like, oh. Thank you, Matt, for honestly, I want to do a straw building extension now, if that's even possible. I don't know if I'd get a mortgage for that, but I want to try it. And thank you, Roy, as well, because I've dreamt about the reuse steel before, because I think I've seen it on a previous event. So I do think, there's possibilities, and it's been really lovely hearing everything that's been said tonight. So I suppose it's all the final thank you. So thank you, Roy, thank you, Rob, thank you, Matt, and thank you to Katie, who's been in the background sorting out all the questions. And then a final note, so Calling All Creative show windows winners will be announced soon, and a date to learn more about the BAA and joining or even running the association will also be put up on our social media soon. And we hope to be bringing you the next event in person, and look forward to seeing you all at the next BAA event. Thanks all.
Thanks,
everyone. Cheers. Bye-bye.